All right. So in the lab so far, what we've covered is essentially we've looked at. I'll share the screen instead. We've looked at the model of what a GAN looks like. We've seen the two different parts of the GAN, which is the generator and the discriminator. How losses don't backpropagate through both of them because they're not connected. So losses backpropagate through both of them, but not the same loss backpropagate through both of them at the same time. Right? There are two different types of loss: discriminator and generator. We also saw the objective function, which we saw from the original paper, how they defined the GAN as a minimax game between uh, two players, which is the generator and the discriminator. And we also saw why the generator samples from random noise, and why the discriminator samples from both the outputs of the generator and the real images created by the discriminator, and the real images from the discriminator. Um, Apart from that, we've been coding the generator so far, and that's what we've done. So that's the brief summary of everything we've covered in the lab so far. So um, just checking the documentation for image.view. Yeah. So we're having to reach. So because we are not using a convolutional GAN here, we're using a plain and simple neural network GAN. So for that we can't use we won't create an image as an image. We'll create an image as a singular vector, and that will eventually we'll have to reshape that to an image, which is what we're doing right now. So image.view creates a 28 by 28 vector of the original 784 by 784 vector. That's the only difference. And we can actually remove this and specify this to be something. We keep it at 100 per code. This one. So now we're going to code the gen. Now we're going to code the discriminator out. So you only need this much code to actually create the image itself. I don't know why this is an issue. Okay, never mind. Again, just definite. And this will also have a similar model. Similar way way as we're defining them, not a similar model. Yeah. So here, as you can imagine, now that we're taking the input from the images, this has to be the size of the image now because we're using MNIST. The first layer will be 784 to whatever we want. So we'll keep it 512. And not leaky. I'll just copy this. Right. So now we are done with defining the model for the discriminator as well. Now we can go to moving, creating the forward function. So here what, okay, not this, but yeah, here what we've done again is we've taken the input image X, which is going to be 28 by 28 or whatever dimension you're using, and we're flattening it into a 1D vector, which is what torch.flatten does. We've covered this in previous labs. After that, we've created a variable val, which is for valid for just a random variable, and that's going to be the probability that the discriminator feels that the image is either true or false. Right? We don't tell it which yet. We will tell it that through the losses that we'll be creating. Um, and through this, essentially, we're able to create the basic framework for our GAN. Does anybody have any questions up until this point? So just to quickly summarize, we've created a generator model which samples from a latent space of 100, which is going to be of Gaussian noise, upsamples it to 1024, and then downsamples back to 784. We're using leaky LU units everywhere because they're just more robust, and we're using TANH here because it's centered. The reason why it's important to have centered units is because if you have non-centered units like a sigmoid, you can't accurately capture in this thing image qualities. You can see that if you, so we'll put a sigmoid there and run it again once, and it will not work. So now we'll just define the losses. So if you think about it in terms of the discriminator, this is essentially a binary classification problem, right? It's either a true image or a false image. So we can use binary cross entropy loss for our loss function here. Now we'll just create our models, change our models. I think I've connected to a GPU runtime. I hope I have. I have not. Okay, so we'll connect to a GPU runtime. So this is if CUDA is available, then we'll put everything to CUDA. It's never this straightforward. Okay, so now we have to configure the data loader. Now that we've put everything to CUDA, now we have to do the data loader. So we've done this many times before. Should not be an issue. So we're just importing the MNIST dataset. This is yellow right now because I've forgotten to import the correct libraries. I'll just do that. Yeah, okay. Batch size of 32. And shuffle. All right, so this is also our data loader, which we are now done with. Are there any questions so far? Okay, seeing none, I'll just take a quick recap. Um, yeah, we've discussed the generator and that twice. So here we're using the adversarial loss as the binary cross entropy loss, which is essentially the loss which for a classification problem, and because it's binary for two classes, you can have cross entropy losses for larger number of classes as well. Additionally, we have the reason why we can use binary cross entropy loss is because for a discriminator, the only thing it needs to do is decide whether an image is real or fake. So it's a 0 or 1 problem for it. Then we pushed everything to CUDA so that we can train on GPU. And then we've created the data loader, which is just using the data loader, datasets.mnist, train equal to download true. We don't need the test set because we're creating a generative model. We don't really have data to test it on. Batch size 32 and shuffle 2. So that's all we're doing. Uh, yeah, after this, we'll create the training loop and then train it. So now we'll just define optimizers. So as you can imagine, we'll need two different optimizers because we have two different models, each of which is going to have its own set of gradients and its own autograd matrix. Right. So now we're done with that. One more thing we need to import. Import. Okay, so what we'll be using now. All right, wait. I'll just write it then explain it later. So valid is uh, insert images dot size 0. Hi, sorry, my laptop crashed. Am I audible now?
Yes.
Yeah. So right, we were at the over here. So now we're creating the ground truths, which is just a long. So why we're doing this is that this essentially helps our binary cross entropy loss function out. As you will see in a second when we pass it through our loss. Um, yeah, that's about it. You will. For those of you who remember the BC loss function, this should be straightforward. So now we're starting the training for the generator. So as we had sort of discussed, they're trained separately. So first we'll go ahead with the generator because we need its input, we need its output for the discriminator to be trained. So optimizer optim underscore g. Not zero that. Set is here we're creating the noise prior. Now we'll pass it through the generator to get the images we need. And now we'll calculate the loss for the generator. It is essentially just the adversarial loss that we had defined earlier, which is the binary cross entropy loss between the prediction of the discriminator gen underscore is valid, which is not discriminator, and the and our ground truth in this situation. So yeah. All right. So this is essentially the generator part. We can now train the discriminator and tracing it to an R. So real images, real loss is again the adversarial loss between the discriminator's predictions on real images versus valid, and the fake loss is the adversarial loss between gen underscore images. So we're detaching them from the gradient because they're still connected to the generator gradient, and they will give us an issue if we don't do this. Now, it's left as an exercise to you to figure out why we're using valid here and here for the generator loss and the real loss. Just answering this question will like strengthen your understanding of GANs by a lot. And finally, the net discriminator loss is real loss. That's loss by 2. And now just lost it backwards. And optimize it. Yeah, now I'm just going to copy the code I've written previously because it's just a print statement. Nothing too crazy. Yeah, 55 and 7. One sec. So this should run now. No, it won't. I missed the commas, which is why there's an error now. You're gonna add those in. This is a capital R, not a small r. To explain what the problem was here. Normalize does it on the basis of a mean and a standard deviation value. But because I miswrote it as a single array, um, I needed to re-specify it as two different. So there is a couple issues that I'm getting here. Um, I think we've configured the data loader wrong, which is why it's not giving us an additional output.
See,
Okay, so struggling with a few more errors, not the best programming there. Okay, so I'm not sure why this is not working. I'm going to go to a previously trained model and show you that. I'm just going through and seeing if I can find that. So to my knowledge, this one was the unaltered model. Okay, so this is working. I will also have the images saved in my drive. So I will open those and show you as well. It is nearly the same code as the previous one. The only difference is that this was built to simulate mode collapse. So the um, results you will see here will not be as good as the previous code. But for some reason the previous code is not working. So I will correct that code and share that with you later. So just something that I wanted to show you, that the entire purpose of creating like the generator adversarial model was to have that objective function, right? And that objective function was a minimax function where the generator wanted to okay, let me just check which one wanted to minimize. Right. The discriminator wanted to maximize the function, and the generator wanted to minimize the function. So for it to be a good GAN in the end, right, these values will have to be sort of similar, and the exact equilibrium is reached at zero point 0.5. So while they're sort of close to zero point 0.5 right now, these are not going to be good quality images because of the fact that the model's not even close to convergence yet. So that is the situation. I'll just open the images and show you that. I'll just download a few images. The images are so small that I can't see them, and this will take a while to train. So I can send you either the weights or I can send you the entire code, and you can run it on your own on your collab. Um, that should be a better way for you to sort of understand what's going on. But the images that are currently there are mostly just black. Very few images will actually have white spots, even pertaining to MNIST on them, and that's because model is not even close to convergence yet. So that's pretty much all for today. Apologize for the problems with the code today, but um, yeah, that's sort of what we're sort of done with the objectives for today. Does anyone have any questions? Okay, seeing none, we'll start with the test then. Just 1 second, Sham, sending it across. All right, just one more thing I wanted to show, which I haven't done yet, are a couple libraries which you could use for um, measuring the effectiveness of GANs. So there is a PyTorch FID. Look up what FID means. Similarly, there are other libraries for inception distance, and these measure the distance between distributions. So if you recall from the paper, uh, the GAN moves towards the original. The GAN forces the generator's distribution to move towards the original distribution. And these sort of measure how far apart they are. So that's what both of these are. And mode collapse is essentially what I was trying to simulate in the earlier in this notebook, which is, if you remember from the lab, uh, of, like, let's say if I've got 12 output classes, or in MNIST's case, if I've got 12 output classes, I'm only able to, my GAN is only able to reproduce, let's say, one, it only the letter zero, for example. So that's where my GAN will fail. That's called mode collapse.